All right, welcome back, all. We have another nice session for Bio 18 ahead of us. And for those who are taking notes or following along with the PDF, the notes on our Canvas Cat Courses page, we're going to look at the Poisson distribution today. As usual, if you wish to know this material on a deeper level, I have typed out some of the more theoretical aspects on the front page. This is another example of what we call a discrete distribution, like how we've been studying the binomial distribution so far. In particular, we're going to say that something happens either 0 time, 1 time, 2 times, 3 times, etc. But this could be, in theory, many, many times. Something can happen many, many times. However, on the other hand, the model or formula we're going to look at today, called the Poisson distribution, tends to be used when something happens rarely, when we expect the event to happen just a small amount of times. Skipping ahead through the theory, we end up with this formula down here: mu to the k power times e to the negative mu divided by k factorial. Mu is our population mean, the average of whatever we're looking at. E is our natural base, that button on our calculator, that's about 2.7183. And then the denominator k factorial, that's the countdown. For example, 5 factorial was 5 times 4 times 3 times 2 times 1. The chat question is: are the lecture notes uploaded to cat courses? The outlines are already there under classnotes.pdf. It's just like what I had in person. They're the outlines, and I hope to go over the actual writing out work today. So again, the Poisson distribution tends to be used to model behavior that we hope does not happen often. So as you can see in front of you, I have statistics about the crime of stalking, how often stalking was reported at UC Merced over this 4-year time span. We are hoping that it does not happen often, especially in a school of about 8,000 students. As a side note, this data is a result from how we are at a public university and the crime statistics have to be publicly available in a matter called the Query Act. So these statistics are reported every year, and I record them for the purposes of giving math problems. At some point, I gotta figure out my cough button. All right, so you can see I have a part A, B, and C. We'll scan through them like we did last time. The first task is to find the mean of the data, roughly. Just get a sense of, on average, how often does stalking occur per year. We're going to take the average as you would have seen in earlier math classes, simply adding up the numbers, and since I have 4 years of data, dividing by 4. Also, before I forget, notice in the instructions I specifically say we're going to assume a Poisson distribution. What that means on the calculation side is literally which formula we're going to use. Down here in part B, I'm asking to compute the probability that exactly 2 stalking incidents will be reported this year. The signal word I'm focusing on the moment, at the moment, is exactly. And the way that plays out, like last time, is that we start off by saying the probability of k equals 2. 2 events, exactly 2. However, this time, because we are trying out the Poisson distribution, the formula we're plugging in numbers into is this one here. So if nothing else, the questions you ask yourself along the way are, what are mu and what is mu, what is k? We found mu in part A, that was the 11 over 4, and we parsed the task at hand, exactly 2, to find the k value. We plug in those numbers here, and as usual, my request for approximate numbers, please round them to at least 4 decimal places. Now, in part C, I'm going to ask a slightly more difficult question. We're going to compute the probability that at least 1 stalking incident will be reported this year. Stalking will be reported at least once in a school of about 9,000 students. So what I want to do is actually kind of take a moment to ask you to think about this in an intuitive sense. When I'm asking what's the probability of that stalking will be reported at least once, do you expect this probability to be relatively large or relatively small? What do you think? And go ahead and type your guesses into the chat window. All right, it was good to take a moment there and get a sense of the probability we're calculating. I'll go ahead and show you the calculations. Excuse me. Just allergies, I swear. The verbose way of thinking about this is that I'm asking what's the probability of at least 1 stalking incident. So that's 1 stalker, or 2 stalkers, or 3 stalkers, or 4 stalkers, on and on and on. Technically, an infinite calculation. And thus, recall when we have this wording, at least 1, we have a clever way of going about it. That to calculate at least 1, what we're actually going to do is calculate the probability of 0 stalkers and then take the complement, the 1 minus of that. Plugging in the numbers here into our new formula that we're trying today. Now, in this particular calculation, I also like to point out, for the sake of reinforcing our mathematics skills, that here in the top left, anything to the 0 power is 1. In the denominator, we mathematicians specifically want you to say that 0 factorial is equal to 1 so that we avoid a divide by 0 situation. So you notice that in this example, the calculation simplified quite a bit. And we end up with an answer of about 94%. Thus, at last, the probability of at least one reported stalking incident is very large. But having taken the time to think about that intuitively, it lets you double check your answer. Were you expecting to get a large value, or were you expecting to get a small value? And I'm going to take a moment as a breather and welcome any more questions from chat. Hail hydrate. The question in chat is, why does 0 factorial equal 1? It's not even mathematically clever. It's just how the factorial or combinatorics happen to work out. Mathematicians literally say, we're just going to say or define that 0 factorial equals 1. It just helps make the rest of the math works out. But there's no real clever reason for it. All right, well, moving on to a second example here. This one, the crime I was studying was drug law violations. Now, in context, drug law violations does not include alcohol or smoking, but are talking about harder or more dangerous drugs, so to speak. So you can see in the table, we get a sense of how often these happen at UC Merced. Once again, in part A, we're going to get a sense of, on average, how often these drug law violations happen. Out of the numbers, once again, there were 4 years of data, and the average happens to be 4 as well. So we expect 4 drug law violations per year. As a side note, this does not take into effect that UC Merced is a growing university. In part B, I'm asking for us to compute the probability that exactly 3 arrests will be made this year. The focus is on the word exactly. Exactly 3 means, in math speak, we plug in k equals 3. I had, once again, it back in the instructions stated at the top that we're going to assume a Poisson distribution. So we're going to try out the formula for the Poisson distribution, plug in the values for mu and k that we just discussed, and we'll get a probability of about 20%. Now you see in part C, a slightly more complicated setting. We're going to compute the probability that at most one arrest will be made this year. So just pause, think to yourself, how do the calculations change for those words at most one? In inequalities, that means that k is less than or equal to 1. In talking about the context, the drug law violations, that means there would be either 0 violation or 1 violation. If we got up to 2 violations, that's already too many. And thus, the way the calculations play out is we look at the k equals 0 case and the k equals 1 case. This was the notion of a cumulative calculation that we started to look at last time. Plug in the numbers, run it through a calculator. Was my usual advice that maybe not now, but before your next quiz or exam, make sure that you're plugging in the numbers into your calculator and hopefully we're getting the same results. And as you can see here, this answer happens to be of about 9%. I'll once again take a breather here and field any questions from chat. For those who understandably joined us a little late, today's material is a bit short in that it's one more formula and more or less review of Monday's topics. We'll probably go about 10 more minutes before my throat gives out. If we were in the classroom setting, you know what time it is. It would be the time I say to open up RStudio and whatnot. I imagine for most of you that would be a bit cumbersome. So what I'm gonna do is I'm gonna do the code in front of you like usual. But I am gonna upload the code to Cat Courses. So if you want to simply be a passive participant and watch me make the graphs, that's fine. The code will be available later today. This example, I admit I wrote 2 years ago. So as of March 12th, which was 71 days into the 2018 year, there were 60 mass shootings in the United States. We're going to assume the mass shootings follow a Poisson distribution. That is, once again, in this context, I wish that mass shootings was a rare event and that modeling was a Poisson distribution would make sense for a rare event. So here in part A, I simply asking to compute the mean number of mass shootings per day. And with the limited amount of information I gave in the paragraph above, that was 60 over 71 days. And when I assign this for homework later, a good check right at the beginning is to double check the units. Make sure the numerator and denominator line up. So now, when the folks who made the R software designed the functions for probability, they wanted some what we call uniformity or some consistency in mind. In the previous sections about the binomial distribution, our commands were d binom and p binom. And now that we're using the Poisson distribution, our commands are either d pois or p pois. This is read out loud in jargon as the density function for the Poisson distribution. In part B, I'm asking, what is the probability that there will be exactly 0 mass shootings today? We're using the Poisson distribution. We'll plug in 0. And we need to get a sense of the average as well, so we type that in. Oops, I forgot to run my previous line of code. Rookie mistake. And we get, for the question, what is the probability there will be exactly 0 mass shootings today? Again, I wrote this question 2 years ago. We got an answer of about 43%. Now in part C, I'm asking a slightly more difficult but more realistic request. What is the probability that there will be at least 1 mass shooting today? So I could see in the comment I have said we want k to be greater than or equal to 1. Which will be the complement of what we just did in part B. Namely the 1 minus the case of 0 happening. For the question in chat, for my students, no, you do not have to submit the code today. No, you don't have to submit this today. So yeah, I'm basically streaming some version of the homework assignment. Now, as we deal with the more cumulative calculations, the one where we want to add up several terms, the commands switch from the letter D as in dog to the letter P as in probability. Now, because at least 1 mass shooting could be satisfied with the notion of 2 mass shootings, 3 mass shootings, 4, etc. To get that going in the direction that the math is requesting, we would set lower tail equal to false. And whoops, put the wrong number there. And what I'm saying at the moment is that these 2 lines of code are equivalent. It's just, as we're starting out, it might be easier to understand this first line of code than the second one. Now, In part D, I'm asking a slightly more difficult setting so that we could see where the changes occur. What is the probability that there will be at least 2 mass shootings today? So this is the probability that K is greater or equal to 2. That means we have to consider the possibility of 0 mass shootings or 1 mass shooting, and then take the complement 1 minus of that. The question in chat is, what does lower tail mean? It makes more sense once we get to the bell curve in the normal distribution. The lower tail, actually, I have a whiteboard in front of me. So lower tail, once again, is a little easier to see in situations where we have a bell curve. And I brought a whiteboard so I could do diagrams when needed. See if this shows up on cam. When we say lower tail equals true, the shading or the inequality goes towards the left. And when we say lower tail equals false, the inequality or shading goes towards the right. Thus, in that previous question, when I asked for at least 1 mass shooting, because larger numbers are applicable, the shading goes towards the right. And in the R code, we put in lower tail equals false. Now, as these calculations become more complicated, you wouldn't necessarily want to type all that out. So there is another way to possibly handle the situation. Oops, got my cam in the way, sorry. Now, what we're going to see in the last half of this code here are some higher level concepts called the probability mass function, PMF, and the cumulative mass function, CMF. I'm not expecting anyone to understand these right away. They're, in my opinion, tougher concepts. But what I'm hoping is that over several days worth of notes, some of the patterns might emerge so that the material will be easier to grasp over time. So what I'm going to do with some more complicated code here is basically make a couple of bar graphs. The question at hand at the top of the screen at the moment is, what is the probability that there will be at most 2 mass shootings today? but we'll graph the Poisson distribution with values going from k equals 0, 1, 2, all the way up to 10. Like before, sometimes I set these code blocks equal to false so that if you knit these right away, you don't run into errors. To get the graphs to appear, don't forget to set the code block equal to true. As my problem description recommended, we're going to set the k values going from 0 to 10, 0 colon 10. Going through some of the technical jargon, the PMF uses the deploy function, like so. And what I want for the bar graphs as a math instructor is to have a couple different colors so you could pinpoint exactly where the mathematical action is happening. This true false flag is just a bunch of trues and falses. I'll show that in just a second. But the question was, in the word problem, what's the probability of at most 2 mass shootings? So this was to tackle the words at most. Then finally, as usual, ggplot will want a data frame. So we're going to put those items inside a data frame. I'll show you the graph in just a second, but I promised myself I'd show you what the true false thing did. For the k values, which are literally 0 through 10, I asked for k less than or equal to 2 for at most 2. And what true false did is amongst those 11 k values, simply says true when that inequality is true. So now looking at the graph, the probability that we have at most 2 mass shootings today are represented in the greenish cyan colored bars, whereas the opposite, more than that amount of mass shootings, would be these highly improbable bars to the right. Finally, there is a concept that, again, you don't have to understand right away. It's something we'll touch upon a few different times. And it's called the cumulative density function, CDF. Actually, that should say CMF. Cumulative mass function. In the R code, instead of dploy, the R command is pploy for the cumulative calculations. Now we're gonna fixate on the notion of at most two mass shootings, but as we added up before, either zero mass shooting, one mass shooting, or two mass shootings, the cumulative notion will take care of the addition for us, the summation for us. We're gonna stop at k equals 2, and I admit I haven't gone through all the computer programming logic, but I assure you, you want two equal signs here. Data frame for the ggplot, and at k equals 2, you could see this one bar highlighted out of all the rest. Let me go ahead and knit this document to see how this is as a whole. We got our notes about how to start plugging in to these dploy and pploy functions. We got these graphs where you could compare and contrast, go back and forth to try to get a sense of how the numbers roll together. And then finally, just the broad question, why is this called a Poisson distribution? For years, I actually believed this. That's because Poisson is French for fish. And when you look at a graph like this one up here, it looked like the side of a fish. Finally, about a couple years ago, I looked it up just to verify. Actually, there was a guy named Poisson. This is named after Simon Poisson. It's just coincidentally that his last name was Fish. Alright, so that was all a mouthful. I will assign homework, but the homework will not be due until after spring break. My plans right now are to handle some more of the administrative side of things. Actually, let me go ahead and turn off the YouTube recording. But I'm going to stick around for a few minutes if you have any other questions. Otherwise, let me thank you for dropping by and say have a nice spring break, and I'll see you later.